Right, so multiple forces. Here's a question for you. You know the net force is what causes acceleration, right? It's Newton's second law. Net force is what causes acceleration. But what's the meaning of a net force? Because in real life cases, you got multiple forces acting on you. And any mass is going to experience multiple forces, not just a single force. It's multiple forces. Case in point, look at this bicycle. There's a push in this direction. Weight is pulling it down. There's a retarding force acting on it. No, a retarding force is not a force that turns you into a retard. It's just a force that retards your motion. So when you have these multitude of forces acting on it, what's the meaning of a net force? Because we have to figure out what the net force is. Because that net force is what's responsible for the acceleration in essence.
Chopping down a tree clean through by hand is a thing of the past. Pulling down a 30-foot evergreen with a tractor makes sense. But not with a 10-foot rope.
I mean,
evergreen with a
tractor is pulling on the tree in this direction, and the roots in the opposite direction. If that's the case, what's the net force acting on? When we're talking about net force, here's what we mean. Imagine that you got two forces acting on this mass, right? The one is pulling it to the right, the other is pulling it to the left. Okay, give him 5 points. He needs the dominant word. All right, so this is the mass, so you got two forces. Okay, what we mean by net force is the sum total of all the forces acting on it. Okay, so what's the meaning of sum total? Sum total means either you're adding these up, so it's going to give you 45 pounds of force, or you're subtracting these two. All right, from daily life experiences, you know, somebody is pulling on this mass in this direction with 25 pounds of force, somebody else pulling in the opposite direction. So these forces get subtracted, right? So there's going to be a 5 pound of force to the right in essence. So when we're talking about force summation, when we're talking about summing up forces, we mean adding and subtracting. So that's known as a summation, right? So force to the right, take that to a positive. Force to the left, it's going to be negative. Net force is a force summation. All right, so this is sigma summation sign. So it says that just sum up all the forces along the x direction. So this is your x direction, this is your y direction. And so that net force, sum of all the forces along the x direction is going to be responsible for the acceleration along the x direction. So how do we do that? Well, you got a force to the right, so that's going to be positive, and you have a force to the left, so that's going to be negative. So 25 minus 20 is going to be 5 pound of force. All right, so that's a force summation. All right, net force is the sum of all the forces acting on a system. Sum of all the forces acting on the mass. The result net force is what causes the acceleration. And so
the dummy contorts and stretches from the immense force. In only seconds, its arm is wrenched off by one of the aircraft, while the other plane drags the broken torso down the runway. Stanley knows the same thing could happen to him, but he's determined not to back out.
We'll make it.
I'm gonna make it.
Okay.
Come on, Dan.
It's time. The pilots gun the engines. The ropes pull tight as the two Cessnas try to take off at the same time, at the same speed, in opposite directions. Their tachometers have already risen to 1,500 revolutions per minute. Remember, the goal is 2,400. Stanley braces against the tremendous force. Now, at 2,000 RPMs, nearly enough to take off. Grimaces as he fights to hold his ground. Barbara watches, terrified and helpless. The tachometers now read 2,200. More than enough power to take off. Stanley has only 200 RPMs to go. Then suddenly, he's pulled off balance. It looks like he's being overpowered. But somehow, he summons all his physical and mental strength to stop the two planes from tearing him apart. Both engines are now revving at a fierce 2,300 RPMs, more than enough for them to be climbing into the sky. And finally, 2,400. Stanley has done it.
Yay for Stanley. All right, let's get back to
per minute. Remember.
All right, guys, what's the net force acting on right now? How would you answer this question if this were a test question? So the net force acting on is 0. All right, you guys will say 0. Absolutely, you're correct. Okay, so how do you know that it's 0? All right, so those of you guys who said 0, you're right. You versus 5 pounds. So how do we know that it's 0? They cancel. They don't really cancel, guys. It doesn't move. It doesn't move. Okay, very good. So far, if you were to answer it this way, you guys would only get 1 out of 2. So what's missing here? What you guys are saying is not wrong. It's just incomplete. Okay, so let me just get in there and then provide some clarification. Net force acting on is 0 because it's not accelerating. Acceleration is 0. So what is a net force? So you just always go back to the definition. Net force causes acceleration, right? If it's not accelerating, net force is 0. Forces cancel. I'll accept that, but that doesn't mean that cancellation of forces is not the absence of force. There are forces acting on this guy. There's net force is 0. That's what it means. In fact, the forces acting on this guy is just so large If I were to take his place, I would literally lose my arms, if not my life. All right, so except the forces are in opposite direction and equal in magnitude. As a result, the net force is 0. So the forces cancel out. If you want to use that term, it doesn't mean that there are no forces acting on them. It just means that the net force is 0. When the net force is 0, what happens? You fall back to the Newton's first law, all right, according to which in the absence of a net external force, it doesn't mean that in the absence of any force, it's an absence of a net external force. So there's an acknowledgement that there may be forces acting on a system, but the net force is 0. That's what it means. The object is going to retain its initial motion. Object at rest is going to remain at rest. So which means that whatever these forces are, a tremendous amount of forces, they're in opposite directions. So the net force is 0 on the horizontal direction. So if you want to say cancel, I'll go along with it.
Their tachometers have already risen to 1,500.
All right, so is there enough force acting on him now? Of course. How do we know? Because he went from rest to something else. Once it's from 0 to something else, that's acceleration.
Revolutions.
So if this airplane under, right, applies a force which is like a pound more than the other one, there's going to be acceleration in this direction. Well, it's crucial that both airplanes apply the same force, because if they don't, then what happens? He may lose his balance, he may end up losing his arms. So all of a sudden, you're doing some really, really dangerous.
Per minute. Remember, the goal is 2,400.
All right, so the net force, if there's a net force, there's acceleration. No net force, there's no acceleration. No net force, law number 1, inertia. If there's a net force, there's going to be acceleration in the direction of the net force. Pick out the best answer. Okay, I see a lot of C's. Give yourself 5 points. C is the best answer. All right, the E is the only answer that makes sense, right? So you got 2 horizontal forces. And in the same direction, there's going to be a large acceleration in that direction. If they're in opposite directions, they can cancel. So E is the best answer. All right. Okay, so let's just put this concept on a bit of a mathematical ground. So I came up with some examples based on my life experiences a little bit. All right, so your car breaks down. So what you have to kind of push the car for a while to the shop, basically. So imagine that your car breaks down about, I don't know, like 100 feet from a shop, and you just get up and you start pushing. All right, so how do you solve this problem? This is going to be problem number 5. A couple of things about this problem. All right, so number 1, you have to do force diagrams. Okay, this is going to represent the center of mass. Usually it's a point. For some reason, I represent it as a ball. I kind of like doing it that way. It's my old personal preference. So notice that there are 3 forces acting on the system. All right, so 2 people are pushing it in the forward direction. F1 and F2 are the pushes. And there's an opposing force, which is known as the frictional force. All right, so F1 and F2 are the applied forces, and lowercase f is the frictional force. Okay, everything is expressed in terms of the metric unit system, so we can just focus on the math. That's the purpose of this problem. Just focusing on the detail of this. All right, so part of A is finding net force. We want it in terms of newtons for physics, and then we want it in pounds for us, and then get the acceleration. And then, so you got these 2 people pushing the car only for 100 feet. So determine the speed of this car in this distance, right? So meters per second for physics, miles per hour for us, at a distance of 100 feet. That's the only thing that needs conversion to meters. And then we'll get it in terms of meters. Okay, so it's that. Okay, net force is the summation of all forces on the x direction. So sum up the forces. F1 and F2 will be positive. Lowercase f is going to be negative. And then the numbers. You got 300 plus 400 minus 600. And you'll get a number. If it's 100, that's going to be 22 pounds. All right, so we end up getting 22 pounds of force. All right, it's actually realistic. When you have 2 people pushing on the car is, net force is about 22 pounds to 30 pounds, no more than that. I don't care how hard you're pushing up against the car because of friction. So net force is what causes acceleration. All right, so mass of the car is going to be 2,000 kilograms. We got the net force, which is 100. Mass is going to be 2,000. All right, this number divided by that is 0.05. All right, that's it. All right, now let's figure out the speed at this distance. All right, so there's acceleration, so that's going to limit our options to formulas that contain acceleration. All right, I mean, you got a few formulas that you can use. The easiest ones to use will be here. All right, so you get to use those, assuming that the acceleration is constant. All right, so quality of your solution depends on the quality of the assumption, because we don't have a lot of formulas in your toolbox at this point. And this is the only formula that you can use in order to solve this problem. So there's an assumption here that the acceleration is constant, which means that the force acting on the car is getting constant, which is not true, but this is going to be a good estimate. All right, so the initial speed is going to be 0, so that term drops out. So when we do our algebra, don't use numbers, you will get penalized. There's a good reason, as you will find out, because you cannot do these problems numerically starting next week. Right, so everything has to be done in the symbolic algebra side. So here's your final equation. All right, so, and then into this equation, the numbers will go. All right, so our acceleration is going to be 0.05. And we got a distance which was 30 something, 30 and a half. All right, so multiply square root. And it's going to give us a number and then convert to miles per hour. That's going to be about 4 miles per hour. Okay, so this is an overview of the way to do these problems. This is almost like high school level physics problem solving. It's probably a little bit more advanced than high school physics level, but it's not quite where university physics is. We are still about a step below where we need to be in terms of quality, high quality problem solving, but we're gradually getting there. So the car is fixed. You're taking the car out for a test drive. And then when you do that, this is the drive force, 1,000 newtons. Frictional force is still opposing the motion. So now we got a few more questions to answer. So what do we got? So drive force is going to be 1,000, and then frictional force is still 600, opposing the motion. Same mass, same car. So the net force acting on the car is what I want. I want it in terms of newtons and pounds, and then figure out the acceleration. And then check to see how far the car is going to move at the end of this time period. Time period is 30 seconds. So the question is how fast in terms of meters per second, miles per hour, 30 seconds later. All right. Any convergence? I don't see any convergence, so let's jump in. And so the net force, once again, sum of all the forces along the x direction. Capital F is positive, lowercase f is negative. All right, 1,000 minus, what is it, 600, so it's going to be 400. And it's going to be, I don't know, 88 pounds or something. All right, so the acceleration is caused by the net force, so we just isolate the acceleration. So net force is 400, mass is 2,000, so it's going to be 0.02 meters per second squared. All right, so this is about 90 pounds. It's going to be 88 in reality, so 90 is good. All right, part C of the question. How fast 30 seconds later? So this thing is initially going at 60 miles per hour, so how fast will it be moving 30 seconds later? All right, only one makes sense to use is this one. All right, you know the initial speed, you know the acceleration. All right, figure out the time. No, figure out the final speed at this time. So this is the one we get to use. Initial speed is not 0. All right, so initial speed is going to be 60 miles per hour. I forgot to list that. It's 26.78 meters per second. So we got all the numbers that we need. So just plug the numbers in. Initial speed is 26.78. Acceleration is going to be 0.02. Time is going to be 30 seconds. And that's it. So this is going to give us a number. It's going to be almost. It's going to be 73.5 miles per hour, give me take. So I'm just going to wiggle this. 73.5 miles per hour is where we're at.